In this lecture, we talk about standard resolution of a group, and we will end this lecture by giving two concrete examples of cyclic groups and compute the cohomology and homology of those cyclic groups. So let us start by laying the groundwork. So say this gi plus 1, this we have talked about before. This is just a direct product of I plus 1 copies of g. So that we write it like this, g0 all the way to gi, so you can see I plus 1, and you have obvious group action, g acts on it, and you multiply g throughout. So the standard resolution of these integers by g is a sequence of homomorphisms like this, and this is the augmentation map. And as we have said before, this augmentation map just takes the coefficients here and adds them up. And the differential is exactly motivated from topology. So in topology we have d composed with d is 0, so this d is say acting on I plus 1 element, so this d is sitting here. So we are going to give this this d index I, so right here. So although it is acting on I plus 1, but we are focusing on this index, and its definition is precisely what it is in topology, the standard definition. You have the summation minus 1 to this component j here, and then this hat means this is missing. So if you give this criteria, then obviously you compose two d's, it would be 0. And basically what it means is that image lies within the kernel. So image lies within the kernel. So what we want to show is that actually this resolution is exact, so image is equal to kernel. So for that we will have to construct another map, say theta I. So we consider another map, so theta I we will say goes in the opposite direction. So theta I goes from this I plus 1 to I plus 2. So notice this index is decreasing, so obviously the element sitting here is zg I plus 2. And obviously the map coming back here has to be di plus 1. So theta I is going in this direction, and this white arrow is di plus 1. So this map is very simple. You just put a 1 in the front, so that will give you I plus 2 components. And this is just a construction to prove that this thing is exact. So now you will you first apply theta I to our this component here, and then you apply di plus 1. So obviously theta I will just put a 1 in the front, but the first element of di plus 1 is minus 1 to the 0, and the 1 sitting here will have a hat on it, so 1 is missing. So this is your first element, and the rest of the sum is just copying here. So this element we are copying right here, but if you look at it closely like this 1 is sitting here, so this again looks like this. So because this hat here and the sum is just di, and then 1 means you're applying theta I minus 1 to it. So this you can bring to the other side. So you have this thing coming right here, and then this portion coming right here, and this just now to this you are applying g0 to gi, to this you are applying g0 to gi, so g0 to gi is sitting here, but that is just a component of this. So this id on, you can say zgi plus 1. So obviously we did this construction to show equality here. So now you start with f in kernel, then we will say that f actually lies in the image, and then we are done. So for f in kernel, you can just start applying f here. So f is in the kernel, so you have f here, you apply f here, you apply f here. So f is in the kernel of di, so this is 0, but this applied to f is just f. So that therefore, so obviously image is f. So as you can see, this is, you're applying di plus 1 to something to get f, so f lies in the image of di plus 1, and that's what we wanted to show. So this was obviously there from this argument. The opposite direction is you start from f in kernel, you back in image. So the lemma is that this resolution is exact, and that's what we just proved, and this theta was the construction precisely to prove the lemma. Now this g module zgi plus 1 is free. So therefore you can, since free modules are projective, you can say that standard resolution is a projective resolution. Now you have a projective resolution. So once you have a projective resolution, we are in the world of homological algebra. So we can apply two functors to it. We can apply the home functor and we can apply the tensor functor to it. You apply the home functor to the resolution, then you can compute, you get the cohomology groups or the Ext groups. These are also known as the Ext groups or right derived functors. And if you apply the tensor functor, you can compute the homology groups, which are also called the Tor functors or the left derived functors. Now again, standard practice in homological algebra, you drop the first term. So let us just first see, you apply the home functor. This is contravariant. So notice this sequence now becomes this. You drop the first term, so z is dropped. So you just have zga, after zg becomes zg2, then zg3, so on. So zgi to zgi plus 1 and so on. So notice that the contravariance. That the tensor is just covariance, it just preserves the arrows. So you have the same arrows, but obviously you have dropped this as in home. And then you have this. So now zg, zg2, zg. So obviously it's going from I plus 1 to I. So I plus 1 to I. Here it's going from I to I plus 1. So this thing is exactly what you see here. So from I plus 1 to I, so from I plus 1 to I. Here it is opposite, from I to I plus 1. So again you see the term z is dropped here. So these are the two important functors. One just needs to memorize them. Every time anyone says home functor or Tor functor or home functor or this tensor functor, one should know. So in this term you have dropped the first term, and that the first term, now the kernel of this map is precisely what is going to give you the 0th homology and 0th cohomology. So here you get homology. So here this is our homology, and this is precisely this term because we have dropped this tensor term. So see, this is not here, has been dropped. So this starts with zg. Similarly here z has been dropped. So cohomology is this, and this we have shown before. This is the term a superscript g and a subscript g. So these are the so biggest submodule which is fixed by g. So this is the biggest quotient fixed by g. So this we have talked about in the very first lecture on group rings. So if you have forgotten, you should see again and memorize this a subscript g and a superscript g. So this is our cohomology group, 0th cohomology group, and this is homology. So you compute the cohomology of this, that will give you these HIs, and you compute homology of this. Essentially this just kernel over image here and kernel over image here. In both the cases it's kernel over image. It's just the indexes are different. Here you have increasing, here you have decreasing. Here you're going from 1 to 2 to 3. Here you're going from 3 to 2 to 1, and here. So that is it. So first example we gave is of an infinite cyclic group. So say G is a group which is generated by T, and obviously you have all the powers of T including negative and positive powers. So this is isomorphic to integers. So this is an infinite cyclic group, and this ZG you should think of it as ZT and T inverse, so Laurent polynomials. So then you have this free resolution. So instead of ZG you should be thinking this group here. So again this group right here also. So this is just multiplication with T minus 1 map, and the augmentation map should be just, so since this is sitting right here, you take f Laurent polynomial and evaluate it at 1. So that will land you right here in integers. So again we have two maps. You apply the tensor functor and you apply the home functor. Obviously you drop this. So this thing is not exact right here, and this thing is not exact right here. So now you can compute homology and cohomology. So this tensor will give you homology and this will give you cohomology. So we have already seen for 0, this is a subscript g, this is a superscript g, and since there is 0 sitting everywhere else, so for greater than 1 you have 0, greater than 1 you have 0. So now you can focus here. So we have already computed 0, so 0 sits here, here H0 sits, here you have H1, and here you have the homology, and here you have the cohomology. So again, this is just multiplication with t minus 1, and now you can see that this this 0 should match with this. So this is same as this because the maps are the same, and similarly here this should match with this. So again, because of the symmetry here, so what is happening here is also happening here. So this matches with this. So these two match because the way these maps are. So this is it. So this is the homology and cohomology for infinite cyclic group. So now you consider a finite cyclic group, so generated by T, which is Z modulo NZ. So your group ring should look like this. So now you take the resolution. So instead of ZG, you should think of these things sitting in place of ZG. So obviously again, this t minus 1 is nothing but multiplication with t minus 1 map, because here the element f is from this ring, and the norm is just the sum of the group elements, because norm is just this group element. So for this ring, because we are saying ZG, generally norm is just sum of group elements, but since this ring looks like this is just these elements. So once you have this resolution, you tensor it, you get this complex, and you apply a home to it, you get a co-complex. Again, you are dropping this term, and again the augmentation map is just function here getting mapped to f of 1. Again, you should think f coming from right here. So there is loss of exactness here and here. We have dropped this term, so immediately the first term is always the same for homology and cohomology. So homology is coming right here, first term is a subscript g. Cohomology is coming right here, this is a superscript g. So now this we have computed, the 0th. Now the first, so first is obviously kernel of this map, which is just elements fixed by g, because you're multiplying with t minus 1 and saying what elements multiplied with t minus 1 go to 0. So those are precisely the elements which are going to be fixed, and then modulo the image, and image is just end a. So that is it's just a definition of homology, kernel over image. So again for H2, now the map going out is n, so you talk about kernel of this map modulo what is coming inside, which is t minus 1a. That is it. Similarly here, so here again, these two are just symmetrical. So what is happening here is just happening here in a different order. So here the arrows are. So if you understand this, the same reasoning applies here, but the way the arrows are going, this thing comes here and this thing comes here. So just think, because these two are symmetric. Or you can just see directly here. Now H0 is for H1, you have this map n, so cohomology is kernel over image, so kernel of n over image coming in, which is t minus 1a. For H2, you require the kernel of this map, which is multiplication with t minus 1, so it has to be the elements which are fixed, because it's the kernel of the map modulo the image coming in, which is n times a. That's pretty much it. So just keep repeating this for odd and even, so just keeps repeating. So that is pretty much it. So we have considered an infinite cyclic group and a finite cyclic group and computed their homology and cohomology.